So in the last class we discussed up to here. So what will happen if we have the spring inside the piston and the piston is filled with uh, suppose we say air, all right, and this piston is not airtight. So the piston is not airtight, all right. So what will happen is that when we apply this force, so air will escape from the various small openings wherever it is available, and from the side of the piston maybe wherever it can escape, it will escape. And thing is that the spring will compress. The spring will get compressed. So the basic thing is that the spring will take the load, whatever load is being applied, that load will be taken up by the spring, and after the spring undergoes certain amount of compression. So certain amount of compression when it undergoes, so the spring constant into that compression is equal to the force which is being applied on the spring. So if we apply more amount of force, more compression. So that is what we have seen and we have discussed in the previous class. Then what we did, instead of air, now we have filled the piston with water. All right, all surrounding the spring we have water. All right, and the piston is watertight, so no escaping of water unless we allow it to. All right, so it is watertight. It is watertight, and we do not allow the escape of water unless we, open some drainage path or something like that. So, basic thing is that there is water and there is no drainage path as of now. So, what will happen when we apply a force? That force will be taken up by the water, all right? Because as we can see in the undrained condition, all right, so whatever pressure is being applied is taken up by the water, all right, and though there is a small amount of volume change, we can consider it to be negligible. We can consider the water to be incompressible. We assume the water to be incompressible, and therefore since it cannot be compressed, therefore the spring is not getting compressed. It is as it is, whatever the length of the spring it is remaining the same. So basically what is happening is that there is no compression in the spring, and therefore the spring is not taking any part of the load. Whatever load is being applied is taken up directly by the water in the pore. So this is the undrained condition what we discuss. So the extreme condition of the undrained condition which we have discussed in the previous class. All right, so here in this case whatever load is applied is taken up by the water and no amount of load is taken up by the spring. Now if we open a drainage, so the water will basically escape through the drainage. All right, while escaping, this spring will be getting compressed. So as we see here, it is getting compressed. So while getting compressed, that means now there is a compression in the spring. So suppose x1. All right, so this is the total compression. So this is the total compression in the spring. This from here to here we have, suppose, x1. All right, so multiplied by the spring will be equal to the force which is being applied. All right, so basically we can say total stress total stress is equal to the effective stress in this case. So whatever load is applied is now taken up by the spring, not the water. All right, so no load in the water, no component of the load in the water. All right, or no pressure in water. All right, so there is no pressure in the water. All the entire amount of load is taken up by the spring, or we can say in other words the entire amount of total stress is taken up by the soil, and therefore the effective stress in the soil is same as whatever the applied total stress on the soil. And then we see that there is a change in volume, and this change in volume is brought about by drainage of water out of the pores of the soil, out of the pores of the soil. So basically, this amount of volume change, whatever volume change has occurred, that is basically the reduction in the void ratio of the soil or the porosity of the soil. All right, so that is the consolidation. That is the consolidation. So this is a drained condition and this is the undrained condition. So there are two conditions which are being most prevalent in the triaxial as well as in situ also. We will see how. All right. So yeah. So this is the compression here. Now, now when we suppose allow the total drainage of the soil, all right, so that excess pore water pressure becomes equal to 0, or we can say the pore water pressure is equal to 0. So in that case, the total stress is equal to the effective stress in the soil because U is equal to 0. So in this case, there is total compression in the soil, all right, total compression in the soil relative to the load which is applied, all right, whatever load we apply. So there will be a consolidation in the soil and the soil will get compressed or consolidated and the effective stress will be equal to the applied stress. So there is a consolidation here, right? Now what we do, now we start from the first step again, all right? So we have the piston in the original position here, all right? We have the spring in the free length position, all right? So basically the compression in the spring X is equal to 0, all right? We start from this position. So the force in the spring is equal to 0, all right? And then we apply a load. We start applying incremental load in this case, all right? So suppose we apply 1 kg, 2 kg, 3 kg and so on, all right? And then at a particular point of load, we have certain amount of compression here, all right? Certain amount. Now we have not gone up to the maximum displacement that it can cause, all right? So we have not gone up to the maximum displacement that it has caused. So we have reached up to a certain consolidation we have reached, all right, and then suddenly we have stopped the drainage, all right, the drainage is blocked, all right, or the drainage is now stopped. Now suppose here we are applying 5 kg load. Now for 5 kg load, the spring should have been compressed up to this point, all right, so that there is to be no pore water pressure if we want to consolidate the soil to the state where there is no pore water pressure. So no pore water pressure. In that case, so we have sigma is equal to sigma dash. So in that case, the piston should have moved from this position up to this position. But we did not allow that. We have not allowed that. All right, we do not allow that. So what we do, we stop at a particular distance, all right, we stop at a particular distance and then the drainage is stopped. So we have a displacement in the spring X, all right. Now the total load which the spring is taking is K into X. Now we say suppose X is such that K into X is equal to 3 kg. So we have k into x is equal to 3 kg. Now what about the remaining load? Now we have 2 kg force. What about that? All right. So that part of the load will be taken up by the pore water. So this is basically a state, all right, where we have written in the previous classes we have seen how if we have a soil element at a particular depth, all right, at a particular depth we have a soil element, and we have a water table at a particular depth. So this is the depth of the water table H, all right, and this is the depth of the point from the surface. So this is the surface and this is the water table, right? So here if we consider here we have a total stress which is equal to the weight per unit area of everything on top minus the pore water pressure, which is the unit weight of water into the height. So we have sigma dash is equal to sigma minus u. Alternatively, what we can say is sigma is equal to sigma dash plus u. All right. So this is the case which is happening here. All right. So we have sigma dash portion taken up by the spring, and we have the pore water pressure, all right, or the pore water taken up by the, or the load corresponding to the pore water taken up by the pressure in the water. So that is the difference of load, or the distribution of the load in the soil and in the pore water. All right. So I hope the condition in situ we can relate to what is happening to the spring and the water in the piston. Now if we open the drainage, definitely that 2 kg load, 2 kg load which was taken up by the pore water, all right, that will be dissipated, and the entire load of 5 kg force will be taken up by the soil, or will be taken up by the spring itself, and instead of being compressed up to here, the soil will be consolidated up to this state, right? So here we have that difference. So instead of being consolidated up to here, we have the spring compressed up to here. So we have this amount of load taken up by the spring, and the rest we have the pressure in the water. So the same thing happens when we apply the cell pressure in the soil sample. Right? Same thing happens when we apply the cell pressure in the soil sample. So if we do not allow drainage, some part of the cell pressure will be taken up by the pore water pressure, right? And some part will be converted to the, or transmitted to the effective stress, or the stresses in the soil skeleton. All right. So that is the basic idea of what is happening within the soil sample, and we need to visualize this, because in the next classes when we will be going to discuss the stress path and how the pore water pressure develops, it will be very important. All right. So here we do not allow the drainage to occur, so that is why there is development of pore water. So if we allow now the drainage, again the pore water pressure will dissipate out, and there will be a total consolidation of the soil, right? So that we can correlate to these two spring, all right. So if we observe these two spring, all right, and we apply a force, so definitely if we apply P, all right, there will be a force P1 in this spring, and there will be a force P2 in this spring, and definitely and obviously we can observe that P1 is not equal to P2, because we have the spring constant of this spring higher and the spring constant of the spring lower, right? So for the same amount of deflection, the deflection will be same for the both cases, all right? So deflection of the Both the spring will be same. Since it is same, so here 120 k kilonewton or Newton per meter into X will be equal to P1, and we have 80 Newton per meter into X, we have P2. So if I divide P1 by P2, so if I say P1 by P2, we have 120 by 80. So P1 is to P2 will be equal to 120 is to 80. So in that ratio, this force P will be divided. So the same thing is happening here. The spring will take some amount of load, or the soil will take some amount of load, and the water will take some amount of load. So the same thing is happening. So that is the distribution of the stresses. So that is why we can write total stress is equal to effective stress minus pore water pressure, or in other words, we can write, sorry, effective stress equal to total stress minus pore water pressure. All right, in other words, we can write effective stress plus pore water pressure is equal to the total stress. So the stresses in the soil plus pore water pressure is equal to the total applied stresses. All right, so that is what we can write. Now up till now we have been applying only compressive load. Now let us discuss what will happen when, now suppose what we have done, we have applied a load, all right, and the soil has consolidated, or the spring has compressed. The spring has compressed, so up to a certain point the spring has compressed or the soil has consolidated, the same thing. Now what we do, so initially the piston was here in this position, all right, in this position. So we applied the load and the drainage is open. So when we applied the load, the water flew out, or it drained out. It drained out, the water drained out. So when the water drained out, the soil or the spring got compressed. So the applied stress is now equal to the effective stress, and pore water pressure is equal to 0. Now what we do, we close the drainage. Right? The load is applied, we close the drainage now. And then we release the load. So we started from this point, we applied the load, let the water flow out, all right, drain out. And when the water drained out, the pore water pressure, no development in pore water pressure, whatever load we applied, that same amount of load got transmitted to the spring or the soil, and therefore we have this condition. And now what we do, we first close the drainage, and then we release the load. Now what will happen? So now what will happen is that the spring, it will try to expand to its original position. So in that case, what it will do is, it will put a force on the piston in this direction. So it will try to push the piston out. Yes or no? Yes, obviously it is very clear. So the piston, the spring will try to push the piston out. Now since there is no drainages, water cannot come into the sample. All right, so water cannot come into the sample, and therefore there is no way to expand the volume of the water. So what will happen? There will be now negative pressure in the water. So the water will pull the piston from all sides into the, or towards, all right, so it will not let the piston move out. So here what is happening, the spring is trying to push the piston out. So we have the piston here, the spring is trying to push the piston out and the water is trying to pull the piston in. So we have negative pore water pressure. All right, so I think this is clear. So, and we have the piston in the I mean whatever I mean here what we have the effective stress is basically we have sigma dash is equal to this one minus the pore water pressure. All right, so the pore water pressure is trying to pull on all sides. All right, from all sides. Now if we allow the drainage, all right, now in this case we did not allow the drainage, so this is again undrained case. Now if we allow the drainage, what will happen, and we release the load, so the spring will move out or into its original position. So it will move out from this position to the original position here. So what will happen is we will have drainage of soil, drainage of water into the soil. All right, so this is the reverse case of what we have been studying. All right, so just the hypothesis, just keep in mind. So what is the effect of drainage cases? All right, in both cases, when there is a consolidated sample and when there is a normally consolidated sample which we are consolidating, we are applying the load and making it we are trying to consolidate the sample, so drainage is out of the sample. In this case drainage is into the sample. All right, now obviously this spring will come up to its original position, all right, when we release the load. But in case of soil that is not the case. In case of soil, we will have some amount of expansion in the soil, definitely some amount of expansion, but it will never come to its original position. It will never come up to its original position. We have already discussed that in the cyclic plate load test. So we see when we load the soil, we are loading it to certain, suppose this point here, we have loaded it to this point. So we have this amount of displacement. We have this amount of settlement. Now when we release the load, we have this amount of expansion. In case of spring, it would have been up to the original position, but that is the difference. All right, so soil, when it is getting consolidated, when we release the consolidation load, or the total load which we are applying, when we release that load, so some amount of expansion or some amount of increase in the volume of the soil happens, but it does not come up to its original position. All right, so in this case what happens is that the soil will remember its stress history. So we say that the soil remember its stress history, right? By observing the soil, by observing the behavior of the soil, we can predict or we can estimate up to what confining stress it was subjected to in the initial condition. All right, so here again when we will load, we will get one curve, one recompression curve. So from there again it will be a Virgin curve. All right, so in case of consolidation, as we see, so we have a consolidation curve. So from there is a release, so some amount of expansion is there. All right, most of the displacement or most of the deformation in the soil is due to the consolidation. All right, so arrangement of the soil particles, rearrangement of the soil particles, so there is drainage of water out of the soil. And then again when we release it, so some amount of expansion, then again when we recompress the soil, so we will know up to what load it was loaded previously. So that is how we term that, how we actually define the over consolidation ratio. Over consolidation ratio. So if the soil is loaded up to this point now, up to this point now, but previously it was loaded up to this point, so sigma initial and this is sigma suppose present, so sigma initial by sigma present is the over consolidation ratio in this case. All right, so in this case, so that is how we know that the soil has been previously loaded up to a more amount, I mean more a magnitude of effective stress. So I hope uh, you have made a pretty fair idea of what will happen when we allow the drainage in the sample and when we do not allow the drainage in sample. Right? So this is a very important visualization, realization that we need when we will analyze the uh, further analyze the test data of the triaxial test. So let us consider one sample here. So let us consider one sample here as we have previously discussed for the unconsolidated undrained triaxial test. So before going into shearing part, the pore pressure development in the shearing part, we first discuss the pore pressure development during isotropic consolidation stage. Right, this is very important. So pore pressure development during isotropic consolidation stage. So again we consider one sample. So now we know that that sample was extracted from a particular depth, so it is at a depth Z, and the water table was at a particular depth H, and when we extracted the sample out of here, so we had a pore water pressure already there, which is gamma WH, and we had a total stress which is gamma into Z. All right, gamma is the bulk density of the entire, all right, or the average bulk density of the entire soil or anything which is above this sample. Now suddenly what happened? Now we know that effective stress in the soil here is equal to gamma Z minus gamma WH. So that is the effective stress state in this soil. So we can say this is sigma and this is U. So when we took it out and we took it out of the sampler as well and we placed it on the pedestal, so the pedestal it is placed in the pedestal it is placed, so all stresses, total stresses on the sample is 0, but we have already a pore water pressure which is pushing out on all sides. All right, so because of that pore water pressure, we have an effective stress which is actually trying to make the sample expand. All right, so how to plot that? So we have, suppose if I plot it in, this is sigma and this is tau. So if I plot it, if I plot this effective stress here, so minus UR, so it will be somewhere here. All right, and what about the total stress? It is 0, so it is somewhere here. Now So this is the point of, so this is effective stress, and this is the total stress, which is 0. This is 0 and this is 0, right? So sigma 1 and sigma 3 is same, so we have the same point here. Here also sigma 1 dash and sigma 3 dash is same, which is minus ur, so we have this. So this is minus ur. All right. Then we apply the confining stress. We apply the confining stress. Now, when we apply the confining stress, what will happen is that, so we had the initial point here. All right. So this is the effective stress and the total stress we have here. Now, when we apply the confining stress or the cell pressure, sorry, we apply the cell pressure, total cell pressure. We start applying the total cell pressure. So starting from 1 kPa, 2 kPa, 3 kPa, and so on. We go on applying. We go on incrementing the cell pressure. We go on incrementing the cell pressure. Now, for some time, what will happen is that, so we are going on incrementing the cell pressure. So the cell pressure point or the total stress point will move in the x-axis, which is the sigma axis. All right. Similarly, the pore water pressure also, it will start moving. Then at a particular sigma c value, at a particular sigma c value, so you keep in mind that the change in pore water pressure in this case need not be equal to the change in the total stress. All right. In the first, in the initial cases, we will see why is that in when we will study the stress path in detail. We will see that. All right. But the important point to note here is that, when we will be going on incrementing the cell pressure in this manner, the pore water pressure also will go on increasing. Ultimately, at a point, we will have pore water pressure is equal to 0, or basically the effective stress is equal to 0. All right. So the effective stress will be 0. So not the pore water pressure, sorry. The pore water pressure will, the effective stress will move in this direction as we apply confining, the cell pressure. As we increase the cell pressure, so also will the effective stress in the soil will go on increasing, and the pore water pressure, it will, from the negative, value, it will go on, it will start to move towards the positive reading. All right. So the pore water pressure, it will start, moving on to the positive reading. So at a point it will reach 0. So sigma c dash will reach 0, and we have sigma c at a particular value. So this is sigma c is applied cell pressure, and sigma c dash is the effective stress in the soil, which is sigma c dash is equal to sigma c minus u, which we are monitoring here. All right. So the pore pressure we are monitoring. So this is the 0 state of effective stress. So we have this difference. Alright, so that is the difference which we have of the pore water pressure and the cell pressure which we are applying. Alright, the cell pressure which we are applying. Then as we go on increasing the cell pressure, the effective stresses will also go on increasing. Now, alright, and we will see that the pore water pressure is now getting constant. It is showing a constant reading. Alright, it is showing a constant reading. Alright, so now from this phase onwards, when we will go on increasing the cell pressure, so we have, when we will go on increasing the cell pressure, the pore water pressure will also go on increasing. Alright, so the effective stress, so suppose we have the cell pressure at suppose 100 kPa. So we have the cell pressure at 100 kPa and we have the pore water pressure at 50 kPa. Alright, so we have the pore water pressure at 50 kPa. So 100 minus 50 kPa, we will have the effective stress as here is equal to 50 kPa. Now as we go on increasing the cell pressure, suppose I increase the cell pressure from 100 to 110 kPa, we will observe that the pore water pressure will also increase from 50 to 60 kPa. Alright, of course, in actual test that we do, it does not increase to 60 kPa. We will observe that it is increasing up to maybe 59 or 58.5 or something like that. But we take, for theoretical purpose, we take it that the pore water pressure also increases to 60 kPa. So ultimately, you see the effective stress state sigma dash, it remains constant at 110 minus 60 is equal to 50 kPa. So it will remain here. Sigma C, it is going on increasing. Alright. So again we increase, suppose 110 kPa to, suppose we have increased to 100 and suppose 30 kPa. So in that case we will observe that the pore water pressure here U. Alright, so this is U here. Alright, so this is U and this is sigma C. So this is sigma C, this is U. So pore water pressure will also increase to 80 kPa. So again, if we see sigma dash C dash, so sigma C dash is equal to 130 minus 80 is equal to how much? We have 50 kPa. So again, it is remaining on the same, but the cell pressure is going on increasing. So what we can say is that the sample, when it was extracted from the in situ site, all right, in situ site, we can say that it was consolidated. To effective stress of 50 kPa. and therefore that consolidation, that amount of consolidation is actually stored in the soil. All right. Now, here, what is happening is that if we now find out what is delta sigma C and delta U, right? So the or delta sigma C is equal to delta 3 if we say. So we can say sigma C is equal to sigma 3. All right. So delta sigma C is equal to delta sigma 3. So here if we find out what is delta sigma 3 here, so 130 minus 110, we have 20 kPa. So delta sigma 3 is equal to 120 kPa. Right? And what is delta U? So delta U is equal to 80 minus 60, which is also 20 kPa. So in your previous classes, we have already discussed about the pore pressure parameters, so B and A. All right. So here we define one particular parameter, that is the B parameter. So here we see B is equal to delta U by delta sigma 3. Okay. So here 20 kPa by 20 kPa is equal to 1. Again in this case also, if we see, so 110 we increase from 100 to 110, so delta sigma 3 in this case from here to here and here to here we have delta sigma 3 is equal to 10 kPa. Similarly, the delta U, the pore water pressure change, delta U is equal to 10 kPa. So ultimately again B is equal to delta U by delta sigma 3 is equal to 10 by 10 is equal to 1. So here measuring the delta sigma 3 or the change in the or the increment in the cell pressure and monitoring the increment in the pore water pressure when the drainage is closed. When the drainage is closed, we can tell whether the soil is saturated or not. All right. So if B is equal to 1, then we can say that okay, the soil is saturated. If the soil B is not equal to 1, definitely it is actually not equal to 1. It is around, for practical cases, it is if it is more than 0.9. All right. If it is more than 0.9 for clay soils, all right, and it is around in the range of 0.98 for sandy soils. So from here to here, if it is ranging, then we can say that the soil is saturated. The soil is saturated. So this is a very important parameter, the B parameter. We need to check it before doing the test. So this plots which I have done is actually a plot of which we call the stress path. So we have here in this case we have only increased the cell pressure. We have only increased the cell pressure. If so in the previous case, we increase only the cell pressure. If we increase the deviatoric load, then what will happen here? So we will have the sigma C dash here and the sigma C here. All right, and when we start increasing the deviatoric load, so we will have the more circle getting developed. And this diameter will be the deviatoric load or the deviatoric stress. All right, so this diameter will be the deviatoric stress. So this is sigma 3 here, and this is sigma 1. So similarly, in the effective stress also, we will get the deviatoric stress. This diameter will be same. The diameter will be same because shear stress or deviatoric stress is, I mean, it is pore water pressure independent. There is no, I mean, factor of pore water pressure in there. We will see how it is the case. We will see when we will study the uh, stress path in detail. So in this case, we will have the I mean the more circles be getting built up one after another. As we go on increasing sigma d value, the sigma d value will go on increasing, and so the shear stresses in the soil will also build up. So we will have one effective stress more circle, and we will have one total stress more circle. All right. So this is the stress path in terms of more coulomb or more circles. All right. Now we have a better way of representing that. When we study that in detail, we will come to that in the later slides. So I hope you have understood the loading conditions. So I think I will maybe if yeah, I will just try to repeat this maybe, so it will be. So we had a sample. We had a sample which was at a depth, some depth z from the surface, and we had the water table which was at the depth h. So we had total stress gamma z and for water pressure this one. So we had the effective stress in the soil minus u, so gamma z minus gamma w into h. So that is what we had the effective stress. Now when we took it out, total stresses are now zero, but this pore water pressure is still there, so it is pushing the sample out. So we have an effective stress which is negative of the pore water pressure. So it is basically a negative effective stress which we have. Let's treat. So it is trying to push the sample out. Alright, so there will be a small, I mean very small volume increase in the soil, but for practical consideration, we will assume that there is no volume change. So now we put the soil in the triaxial cell, all right, and now we have the sigma c is equal to 0. The cell pressure is equal to 0. So the cell pressure is equal to 0, and the effective stress is minus ur, all right, or the whatever we have the pore water pressure, so negative of that pore water pressure we have that. Now as soon as we will apply the cell pressure, we will go on increasing the cell pressure slowly 1 2 3 4 5 kPa, and slowly we will go on increasing. So also the pore water pressure reading. So if we read the pore water now, if we start the pore water pressure reading from here itself, we will get a negative reading. All right. Then when we monitor the pore water pressure, when we will start monitoring the pore water pressure, so here what will happen? So we will go on applying the load. We will go on applying the load. So ultimately at a particular load, so we have, suppose we have loaded it up to 100 kPa. All right, so 1 2 3 4 5 6, and similarly we have loaded it up to 100 kPa, which is the cell pressure now. So sigma C is now 100 kPa. So sigma C is now 100 kPa. All right, and we measure the pore pressure at that point. When we apply cell pressure, sigma C is equal to 100 kPa. At that point, when we measure the pore water pressure, it is showing a reading of U is equal to 50 kPa. So that means the effective stress in the soil, sigma C dash in the soil, is 100 minus 50, which is equal to 50 kPa. So that 50 kPa will be, yeah, so this is the effective stress state, and this is the total stress. Now, if I increase 100 kPa from cell pressure 100 kPa to 110 kPa, so what is the del sigma C? So del sigma C is equal to 100 minus 110 minus 100, so we have 10 kPa del sigma C. And we observe that the pore water pressure is now showing 60 kPa. So pore water pressure was 50 kPa initially, and we will observe that pore water pressure is now showing 60 kPa. So what is delta U? Delta U is equal to 60 minus 50 is equal to 10 kPa. Then if we increase 110 to 120 or 130, suppose we increase to 120. So from 110 we increase to 120, so del sigma C now we will have again 10 kPa. Here also we will observe that U has increased to 70 kPa. So basically sigma C is remaining constant. The effective stress state is remaining constant. So whatever load we are applying, since it is an undrained condition, so the effective stress state is remaining constant. What is increasing is the pore water pressure, and we then here what we define is the Scampton's B parameter, which is equal to del B is equal to del U by del sigma. So in this case also we have equal to 10 by 10 is equal to 1. Now if we note that B is equal to 0.5, so what can we say in that case? So when we say B is equal to 0.5, what will happen? So in that case, if I increase sigma C from 100 kPa to 110 kPa, what will be the increase in pore water pressure? So pore water pressure will increase from 50 kPa to 55 kPa. So it is half of del sigma. So del U is 0.5 times of del sigma C. Alright, so there will be an increase in the effective stress now in this case. Since only 5 kPa has increased pore water pressure, therefore the other 5 kPa which we have increased, that will be causing an increase in the effective stress of approximately 5 kPa. So of course in reality when we do the practical test, these are all theoretical assumptions which I am showing. Alright, but they are very close, and the the behavior of the soil is mostly in this manner only. Only thing is that it is not always 1. So if we consider 0.9 for clay soil, as I have said, and 0.98 for sandy soil, we can assume that the soil is saturated. All right. So B parameter is a very important parameter. So that is what is the physical significance of the B parameter here. All right. So we have not yet applied delta sigma 1. We have not yet applied delta sigma 1. We will apply delta sigma 1 in the next class. So if you want to discuss something, you kindly please discuss, because it is very important. And if you have different idea, some different perspective, kindly please put forward, because I think it is very important. This step is very important to move on to the next step. So yeah, I am listening. If you have not got the idea, if you have not, I mean, some confusion is there. Okay, what you do is you let the things sink in, go through all the videos which I have uploaded. Even this one I will upload, so you go through that. All right. And whatever, I mean, doubt crops up in your mind, you ask me and we will clarify that. All right. And yeah, so I think the B parameter, it is very easy. So thing is that undrained condition. So in if it is drained condition, if it is drained condition, definitely. So here, as the case was, so as we have increasing sigma c, so we are applying sigma c. So when we will apply sigma c, all right. So yeah, so pore pressure development. So here we see that the volume change, the volume change in the pore fluid, it is very less compared to the volume change due to drainage. All right. So due to drainage, whatever is the volume change, that amount, it is very much less. I mean, when it is in an undrained case, whether due to the compression in the pore fluid. All right. So in for, I mean, majority of the cases, what we consider is that here the compression of the fluid is very much less to the compression in the soil skeleton. All right. So this is not the compression in the soil solids. All right. So it is compression of the soil skeleton. So with the drainage of the water has to drain out. So only when the water will drain out, then we will have the consolidation of the soil. So in that case, there will be reduction in the void ratio or the porosity. So the volume change in this case, all right, volume change in this case is way higher than the volume change due to compression of the pore fluid. So that is why we assume that the pore fluid is incompressible. So in that case, this value is very much smaller than 1, and therefore it is almost, we consider B is almost equal to 1 for saturated soils. For saturated soils. So that is the important part of the this the consolidation stage. All right. So before going on to the shearing stage, we need to learn a little bit about the void ratio as well. When there will be negative and when there will be positive pore water pressures development. So here during cell pressure application, since it is always in the compressive, I mean stress, it is always compressing the soil. All right. So the pore pressure is always development, delta U is always in sync to the delta sigma C. All right. So if we increase the cell pressure, pore pressure will increase. If we decrease the cell pressure, pore pressure will decrease. All right. But then again, we will see that there is a limitation there, as we have seen in the case of the spring here. All right, so in if it was spring, it would have been, it reverted back to the original position. But in case of soil, it is not like that. So in case of soil, there is a permanent deformation and there is some elastic deformation. So when we will release the load, the sigma 3 load, when we will release the sigma delta sigma c load, all right, the cell pressure, in that case, the soil will get consolidated. So when we will release it, so the entire amount will not be reverted back. So the soil will get consolidated, and that amount will be, it will be stored in the soil as a, I mean, it will the soil will remember that stress history. All right, so that is what we term it as the over consolidation ratio. So the next time when we will load the soil, we will come to know, because at that point it will again change the behavior. All right, so in this case it is this one, and this is the recompression curve. So this is the recompression curve here, and this is the normally consolidated curve. All right, so in this case we will know that this is the over consolidation stress. All right, so it has been loaded to this stress previously, so from now on again it is getting consolidated. So there is again rearrangement of the soil particles, and there is drainage of pore water out of the soil. So these are some important considerations. Kindly go through this, and we will definitely discuss it in detail again. All right, so but at least the whatever it is happening, you kindly go through this, and if there is any doubt, you kindly ask. All right, so we will discuss the next part in the next class, that is critical void ratio, and we will shear the sample now. All right, so in the next class we are going to shear the sample, or we are going to apply the deviatory load.